In general, we focus on the spectral pattern analysis, although there is another diversification of this one is as a spatial pattern recognition, in which the shape, the size, and these type of things are considered when we go for that. In this image classification, we will learn about the spectral pattern recognition. When we perform the image classification, the image will get converted into a thematic map. It will get converted into the land use land cover LULC map. Now, when we talk about the classification, it can be subdivided into different types like hard classification and soft classification. Means when we say hard classification, the category or when the classification takes place, every pixel will be assigned just only one land use land cover class. There will be a single LULC in that case. But when we go for a soft classification, it is basically something which consider the fuzziness, the vagueness in the nature. So the nature or the natural features have vagueness. There is no well-defined things over there. That's why the soft classification is better, but it is very complicated procedure. It is quite computationally intensive process through which we can carry out the soft classification. There are the classifier, like there is a fuzzy classifier through which we can perform this task, but still majority of classification goes on in the form of hard classification, where there is a single LULC category assigned to a pixel. So when we talk about natural feature, for example, the forest and the urban or the built up area, or you can say the water body, all these are the natural features, forest, water body. And when you see their boundaries are not well defined like any human structure. When you see the human construction, it all usually has a very well defined boundary. But when we see the land use land cover in these type of cases at the boundary location, there is a mixture. There is no certain one class. There is a gradual change in the LULC classes over there. But because of the simplicity and easy to understand the output, we go for a hard classification. Whatever you see, like if you see the topographic map or if you see the LULC map, all these are the hard classified map. Okay. Thereafter, in the classification itself, there can be a two type of classification. There can be, when we go for a hard classification, it can be a supervised classification or unsupervised classification. So, supervised, unsupervised is just like whether you are performing a training to the machine or not. So, you may have this supervised, unsupervised thing in some other subject in your bachelor's program also, because it is a simple learning technique. So, whether you belong to computer science or electronics, you may have learned, means for CSIT they have definitely learned about these learning procedures. Okay. So first one is the supervised classification. In this one, we first carry out the training. We have seen this one, basic steps of supervised classification. Okay. So when we have a data, we have to perform first training of the classifier. Okay. So training, after the training stage, there will be a classification stage, and finally from the classification, there will be an output stage. So this is how the whole supervised classification takes place. Got it? In supervised classification, we have covered in detail the very first stage, which is a training stage, and we have to discuss it more today. And thereafter, we will go for the classification stage. Now, coming to the training stage, it means the analyst identifies representative training areas and develops a numerical description of the spectral attributes of each land cover type of interest in the scene. Okay. So, this is the training stage. In training stage, when we carry out the supervised classification, what we do? we give these samples. Okay, we give these samples for the training. That is why it is said that there is a need of familiarity with the image scene. Whatever image scene you are using, you must be familiar, you know about that area. How you know that area? There are different ways. Like you can take the topographic map, through that you can get the information of that place. You can use some of the high resolution images, like you can go for the digital earth, like this Google Earth. Over there, you can see what type of land use, land cover is present in that study area. Because it is not always necessary that you will take some place from the India only. You can say some place from the abroad also. So basic way through which we can understand our study area, we can gain knowledge about our study area wherever we are carry out the classification. There can be a topographic map of that area. There can be some, we can use some Google Earth. Another thing is field surveys. Okay, in situ data collection, like means we go to the field. In situ means this might be a new term for you.
On the site.
At site.
Yeah, on the site. In situ means you will visit your site, and from there you will collect the information of that place. Okay. So first we will gather the information of our study area. Once we gather the information, we will know what type of land use, land cover are present over there. For example, in the Prayagraj city, when you see the image, when you open the image of the Prayagraj, you will know which type of, okay, which type of LULC are present in this scene. Since we are familiar with this one, why we are familiar? Because we have the topographic map, because we have visited Google Earth also, because um, because we, you know, earlier, because I have, not all of you, but because I have earlier carried out the work on this study area, that's why I have the knowledge of this Prayagraj city. So once you have the knowledge of that one, once you gain the knowledge of this area, what you will do, you will take the list of land use, land cover classes that are present. So I have given the list of five, like built up, water, vegetation, open land, barren land. So these are the different land use, land cover that are present in my study area. And once that thing is done, once all the land use, land cover classes are identified, the next step is to take the sample. Why we are taking the sample? Because we need to learn what that thing is. We need to train our classifier. Okay, like suppose, you know, suppose I'm trying to train somebody regarding the colors. If a person is not able to identify a difference between the pink color and a red color, so suppose there is some person who does not know a difference between the red color and pink color. So how would you train that person? What is the pink color and what is the red color? You will show that person some of the samples, isn't it? You will show that person what is mean by the red color, what are the different shades of the red color. Then you will show the different shades of pink color. So after giving a set of samples of pink and red, you hope that person will identify the difference between the red and pink, and that person will be able to recognize which one is a red color and which one is a pink color. This is how we try to train a person. Similarly, when we are using a classifier, we are trying to train that classifier. So if we are showing a different shades of red, we are showing different shades of pink to another human being, so that person could able to recognize the difference between these two colors, so that person will able to understand the meaning of these two colors. Similarly, we will give sample to the classifier, so that classifier will understand what is built up, what is water, what is vegetation, what is barren land, what is open land. Okay, since there is a spectral pattern recognition, means we are basically trying to find out what is the spectral, what is the color, what is the DN values in the pixels over there. So therefore, we will get this information from there. Now, there are some rules when we are giving samples. Okay, just wait for a minute. There's some internet issue at my end. Okay. So coming to the training samples, so when we carry out the supervised classification, there is a need of a prior knowledge of our study area. Okay. Now, depending upon the type of classifier we are using, we will start giving the samples. Like if you are using a parallelepiped classifier, it will come in this lecture later on. But when we go for that one, when we go for a parallelepiped classifier, in that case, yeah, just wait. Okay. Am I audible?
Yes, ma'am.
Yes, ma'am.
Okay. It depends upon the classifier that we are using. For example, suppose we are using a parallelepiped classifier. In case of parallelepiped classifier, the classification is the minimum and the maximum value. The extreme values of each LULC classes are considered. So if such type of classifier is used, we need to make sure that no outlier is present in our data set, because if the outlier is present, the whole classification will become incorrect. So it depends upon the type of classifier that we use. According to that also, we will take care of the training sample. But there are certain rules, there are certain characteristics that we need to take care of when we are taking training area. First one is sample size. Okay, so when we talk about a sample size, as such, there is no fixed rule that you have to take this much number of means samples, but there are general things that we need to take care, like sample size is related to the number of spectral bands whose statistical properties are to be estimated, the number of those statistical properties, the degree of variability present in the class. Classification accuracy tend to improve as sample size increases. However, neural based classifier appear to work better than the statistical classifier for small training set, though better results were achieved when training set are proportional to class size and variability. Like an example is given over here, like there is a forest. So spectral subclasses arising from variation in illumination, there can be shadowed and directly sunlit. Spectral subclasses arising from variation in species combination, like 10% oak, 90%, 10% pine, 90% oak, 50% pine, 50% oak. Spectral subclasses arising from variation in density, sparse forest, dense forest. So what they are trying to say in this section about the sample size, so it depends upon the, how many bands are there, which type of statistical property that we are going to measure. On the basis of that, the sample size is taken. But in general, practically, when we carry out the classification, what we used to think, this diagram means what type of variations are present in the data, and according to that one the samples are given. Okay, the samples are given on the basis of number of variations, how many variation exists. So an example is given over here in context of forest. So how the subcategories of for the forest can be given. So first one is given on the basis of illumination condition, like some area is falling in the sunlit region, another area is falling in the shadowed region. So there are two variation on the basis of illumination condition. It is not always like directly shadowed, like something is coming in more sunlit region or some of the areas which are appearing more bright. There can be some brighter vegetation, as you can see it over here. Okay, you can see the difference. See, see this place where I'm placing my cursor right now, and this place and bottom left corner. In the bottom left corner, you can see that the vegetation at some of the places is not that much bright. There is a variation that exists over here. So whatever is the illumination condition, we need to make sure that all sort of illumination condition should be taken care when we are taking a sample. Second is what type of species exist. So I have shown you in the previous term the example of deciduous and coniferous trees in the Lillis and Kiffer book. So I hope all of you remember that spectral reflectance curve that we have seen in the previous lecture, that how the deciduous trees and coniferous trees varies, isn't it? So the deciduous were appearing brighter in the image as compared to the coniferous trees. Why? Because of the spectral reflectance. It is more in the deciduous and lesser in the coniferous. So this is what we have learned through theory. Here also, when we are carrying out the classification, we need to make sure that what type of variation exists. How do we know what type of variation exists? Because we shall study about our study area in detail before carrying out the classification. Supervised classification is not like that one fine day we get up and open the software and start giving samples. It never happens in that way. Okay, for the accuracy of the classification, for the better result, we need to know what type of variation exists in our study area. What type of plants are there? What type of vegetation is there? Is there any variation? So if you know that information, only then you could give all sort of variation, like it is given on the basis of species. Another variation is dense and sparse on the basis of density of vegetation. So as you know, at the center or at the outside the city, there will be more dense vegetation. And if you see around the city, like inside the city, if you see, there is a small patches of vegetations over here. Small patches of vegetations are present over here. So we need to make sure that even some of the sample of this type of vegetation should also be taken, because it is showing sparse vegetation. And if you go to the outskirts at this region, okay, at these places, so these are completely vegetated areas. So there is along the roads there is a built up region, but other than that you can find that all this portion is completely vegetated. So we will take a whole combination over here, a whole combination of variation in any of the land use land cover class. Okay, so this is first thing. Second thing about the number of pixels, again as such there is no hard and fast tool, but in general when you start taking all the variation of this all the variation within class variation, then automatically there will be large number of pixels that you are going to take for the training, but at least 100 pixel per category is suggested. Shape. So when you are giving a sample, again there is no, the shape is not important. You can take any, like you have seen how I was taking the samples in the previous lecture, isn't it? So what was my shape? My shape was completely random. Okay. My shape was completely random when I was taking the sample. So that's why the shape of the training samples is not important. You can take any type of polygon. Next thing is location. Again, location and autocorrelation both are same almost. That when we take the sample, the location should be taken care of. The training samples must not be clustered together. Like, suppose if I told you to take the sample of the water and take 5 samples, so you would say, who will take so many samples? Just create 5 polygon around this place. That's it. So when you do such type of thing, the proper within class, what we say intra-class variability will not get captured. And since this is all are these all are the examples of spatial data. These all are the spatial data. With the spatial data, we already know there is a property called autocorrelation. As per the Tobler's law of geography, everything is related to every other thing, but nearby things are more related as compared to the distant one. This is what we have learned in the GIS technology course. Therefore, because of the autocorrelation property, the samples, if you take from the nearby places, they are more or less same. They will be similar in nature. That's why it is usually suggested to make sure to take the data, to take the samples in a well distributed manner. As we have learned in the interpolation, isn't it? In the interpolation also the sampling step, the very first step is the sampling and thereafter the interpolation is carried out. In the sampling, you have learnt about these things earlier in interpolation, and here also we are taking the sample for the classification. Those basic things need to be taken care of at this place also. We also need to consider that there will be autocorrelation property, and because of that one, we need to take the samples in a very well distributed manner. Throughout the whole image scene, the samples need to be taken. Yeah, there is the last point is good, that the degree of autocorrelation will depend upon the nature associated with adjacent pixels, the pixel dimension, the effect of any data pre-processing. When we have, like in the Sentinel, we have 10-meter resolution. RGB NIR in Sentinel 2A, the resolution is 10 meter. If you take the Landsat image, it will be of 30-meter resolution. If you take some other, it may be of more coarser resolution. So it depends upon what is the resolution also. The second point over here, the pixel dimension is also important. So if you take a very fine resolution, say 1 meter resolution, 0.5 meter resolution data, the autocorrelation will be more prominent among the pixels. Why? Because the pixel size is very small. But if you go for the coarse resolution, like 100 meter, more than that, even the meteorological satellites, they all have a very poor resolution because they need to cover a very large portion of the earth, and the temporal resolution is also very good. So in such type of images where the pixel dimension is very large, the autocorrelation will be comparatively less among the adjacent pixel. Why? Because the size of the pixel itself will be very large, from 100 meter to 1 kilometer, something like that. But if you have a very fine resolution, in that case, obviously the spatial autocorrelation will be more. Okay. Next is outlier. What is outlier? Outlier is the extremely high or the extremely low values. Outlier is the name of a book also. Does anyone read this book, Outlier? Who was the author of this book? Outlier is a very popular book. Anybody know about the author name of this book, Outlier?
Malcolm Gladwell.
Yes. Yes. Yeah. This one is the name. This one is the book, Outliers. by Malcolm Gladwell. So this one is a very popular book. Those who are interested in reading, they can read this book also. This is about the people who are very, they are outlier. They are very, very more successful as compared to the normal people. So this book is about outliers. So we are not going into that one. We are coming back to our image. In image, there can be outlier like this. See these pixels. Where I have placed my cursor, see these pixels. Obviously, these pixels are outlier over here. It is appearing very clearly that these pixels are outlier. Their value is quite, means their appearance is quite different from the here also you can see that there is some pink color. There is one, there is one black color pixel over here. In this whole vegetated area, there is one single pixel which is very clearly appearing in a completely different color. So we are not 100% sure that they will be outlier, but from the appearance, it is appearing that they are outlier. There is some sort of error in the data set. Here again, you can see there are some of the pixels like this one. Whenever we are taking a sample, we make sure that such type of outliers are not present in the sample data. Always make sure that these type of outliers should not be present in the training sample, because if you take, then there will be incorrect result. Like if you take this pixel in the vegetation and there will be some classifier that is taking the extreme value, minimum and maximum. Okay. If any classifier is taking minimum and maximum as the basis of classification, so for these black color pixel in the vegetation will disturb the correct minimum value, isn't it? It will give incorrect minimum value. It will not represent the minimum value of the vegetation because they are not vegetated area. That's why whenever we are taking a sample, we make sure that such type of outliers should not be present in the dataset. So in the extraction of training sample, the presence of atypical value is a common source of error. For instance, one or more vectors of pixel measurement in a given training sample may be contaminated in some way. Hence, the sample mean and variance covariance metrics for that class will be in error. So this is all about the samples. The next topic is about the idealized sequence for selecting training data. So we have already discussed it a lot. I'm just reading out this section. Okay. The whole thing is just same. Few of these steps are different. So see, if when you are carrying out this training, when you are selecting the samples, what should be the ideal sequence? The first thing is sample information, means you need to collect the information about your study area. Sample information, assemble information, including maps and aerial photographs for the region to be mapped. Second, conduct field studies to acquire first-hand information regarding the area to be studied. The amount of effort devoted to field studies varies depending on the analyst's familiarity with the region to be studied. If the analyst is intimately familiar with the region and has access to up-to-date maps and photographs, additional field observation may not be necessary. Third, carefully plan collection of field observation and choose a route designed to observe all parts of the study region. Maps and images should be taken into the field in a form that permits the analyst to annotate them, possibly using overlays or photocopies of maps and images. It is important to observe all classes of terrain encountered within the study area as well as all regions. The analyst should keep good notes, key to annotation on the image and cross-reference to photographs. If observations cannot be timed to coincide with image acquisition, they should match the season in which the remotely sensed images were what they are trying to say in the third point. In the third point, what they are suggesting that in step 1 and step 2 you are getting familiar with the study area. Thereafter, what they are saying in the second step is to collect field observation, to collect in situ data. Means we need to update our information. So that's why what they are saying, that we need to make a plan. Whenever we make a field visit, we need to make a very good plan in whichever field you are, whether you are doing some journalism, whether you are doing some survey, or whether you are performing so this type of image analysis. What route we are following on the ground is very important, because the route planning will decide what type of land use land cover classes that we are going to encounter with. So first of all, there is a need to make a very good route plan of the complete study area, so that all the major things would be visited. And thereafter, they are suggesting how to carry out the field survey. That the analyst need to carry the maps and images that he or she has, and take them to the ground and see whether they are matching with the field observation or not. Okay, whatever thing is present on the field, whether they are present on the map or on the images or not. So that's why they are saying that there is a need to annotate, there is a need to cross reference what is present on the ground. It is not just only important for the collection of sampling data, it is also important when we are going to perform accuracy assessment, when we are going to do the validation of our image classification, because image classification itself is incomplete unless and until it is followed by the validation step. So if you carry out the classification, you need to validate your classification. We will learn about the validation part, about the accuracy assessment part later on. Okay. In upcoming lecture sessions, we will cover to that. We will come to that one. But when we are doing that thing, we need to have this ground information. We need to have the ground truth. Okay. There is a term called ground truth, what is present in the ground. So ground truth could be collected again in different manners. It could be done by field observation. It could be done with the help of maps. It could be done with the help of images. So when that is what they are saying in the third step, that when we go for a field observation, all the information, what is given on the map, what is given on the image, and what is actually present on the ground, it need to be noted down. Fourth step, conduct a preliminary examination of the digital scene, determine landmarks that might be useful in positioning, training fields, assess image quality, examine frequency, histogram of the data. Role of histogram in sampling. Should we check the histogram of the sample data? Yes, this is a question from all of you. Should we check the histogram of the sample data set? Yes, Alok.
I'm not able to relate, ma'am.
You are not able to relate. Yes. What does this mean? You have a sample data. You have a histogram of that sample data.
Mhm.
Ideally, how that histogram should appear. In which case, you will say on the basis of histogram that this sample data is not correct.
Ma'am, ideally it should cover 0 to 255, all the values, ma'am.
Mhm. No. Yes, Arun?
यस मैम। मैम अगर हम सैंपल डेटा सेट का अगर हिस्टोग्राम लेते हैं तो मैम एक चीज़ तो पता लग पाएगा कि उसकी वेरिएशन क्या जा रही है मैम, कितनी बार रिपीट हो रहा है। तो मैम इससे थोड़ा बहुत हेल्प मिल जाएगा कि समथिंग मैम जैसा नहीं होता है कि अगर हम वेजिटेशनल एरिया एग्रीकल्चर एरिया कोई है तो जहाँ जहाँ हमने सैंपल कलेक्ट किया है अगर उसकी रिपीटेशन सही जा रही हो, इमेज से मैच करते हैं मैम की, तो मैम एक गेस कर सकते हैं शायद हो सकता है ऐसा कुछ।
इमेज से कैसे मैच करेंगे?
मैम जैसे कि सपोज कि वो इमेज में मैम येलो कलर में समथिंग दिख रहा है मैम, और मैम उसकी वेरिएशन काफ़ी ज़्यादा है कि पूरी इमेज में येलो कलर से दिख रहा है, और हमने जो मैम हिस्टोग्राम में उसकी वेरिएशन भी ज़्यादा है, तो मैम शायद कह सकते हैं कि हो सकता
इमेज में येलो कलर से दिख रहा है और हिस्टोग्राम से उसको कैसे रिलेट करा रहे हो? चलिए नेक्स्ट, भगत।
यस मैम।
बताइए। अरे बहुत बेसिक आंसर है इसका। हिस्टोग्राम अगर आपने देखा, हिस्टोग्राम में ऐसी क्या चीज हो सकती है जिसको देख करके आप कहें कि ये जो सैंपल है ये सही नहीं है? आपने वाटर का एक हिस्टोग्राम बनाया, आपने आपने वाटर का एक हिस्टोग्राम बनाया, बिल्टअप का हिस्टोग्राम बनाया, ठीक है। आप हिस्टोग्राम देख करके कैसे बता सकते हैं कि ये वाटर का जो सैंपल लिया गया है ये गलत सैंपल लिया गया है? हिस्टोग्राम में ऐसा क्या प्रेजेंट होगा जिसको देख करके आप कह सकते हैं कि ये जो सैंपल है वाटर का ये गलत है?
मैम डीएन वैल्यूज।
क्या डीएन वैल्यूज?
मैम वाटर का रिलेटेड टू अदर मैम बिल्टअप एरिया से कम हो डीएन वैल्यू पे आना चाहिए ना।
ओके।
तो मैम उसी हिसाब से मैम पता चल जाएगा ना कंपेयर करके कि कौन सा, मतलब अप्रोक्स हमें तो पता रहेगा ना कि इतने से इतने के बीच में लाई होना चाहिए हिस्टोग्राम उसका।
ठीक है, ये एक पार्ट सही है। और क्या बताएंगे?
Ma'am, it depends upon the frequency of features how it occurring in the histogram.
Yeah, I think so. This is what Alok is also saying. That we will see the DN range, one thing. What will be the another thing? We need to make sure that the histogram should be unimodal in nature. Okay, this is what I was asking. The first part is also correct, that when you see the histogram, like for the water, the histogram, the DN values is usually lower as compared to the built-up area. If you see the DN values of the water, it is at the lower end. So in whichever band you will see, the built-up will have the higher and the water will have the lower DN value. Apart from this one, what we used to see or what we used to check or ensure that our histogram should be unimodal. There should be a single peak in the histogram. If the histogram of the sample data will have more than one peak, in that case, it is definitely not correct, and the sample of the correct means there will be some sample which is not belonging to that class has been taken. You cannot say that the range of the DN value will be 0 to 255. No, we are talking about a sample, not about the complete image. We are not talking about the enhancement thing. We are talking specifically about the samples that are collected for the image classification, isn't it? So when we are saying this thing that the samples are collected for the classification purpose, so histogram of each sample will be of a one particular feature only. It will not be of all the features. Like, it is not a histogram of the complete image. It is a histogram of a single sample. It will be a histogram of only water, of only vegetation, of only built up. So when we are saying this thing, so earlier when we were learning about the histogram, what we have learned, that for one feature that there will be a single peak, there will be unimodal histogram, and if more than one dominant features are present in the image, the histogram will be multimodal in nature. The same thing is also need to be taken care of, that when we are checking the sample, it should be unimodal. Okay, so coming back, just wait for a minute. Okay, so yeah, so determine landmarks that may be useful in positioning. Then the fifth one, identify prospective training areas using guidelines proposed by Joyce and outlined here. Size of the prospective areas must be assessed in the light of scale difference between map or photographs and the digital image. Yeah, this thing is very important. Many times there is a confusion. Why there is a confusion? Because the size of the map is different, because, or you can say the scale of the map is different, the resolution of the image is different. Okay, so there will be a difference among them. And many times what happen, when you see that thing on the map, you will get confused that it is appearing so small on the map, so big on the image. There might be some mistake from my end. So you need to make sure that there is a difference among the scales, among the resolutions. So the size might be different in different type of data. So this is what they are saying over here, that this should be taken care. 6. Display the digital image, then locate and delineate training areas on the digital image. Be sure to place training area boundaries well inside parcel boundaries to avoid including mixed pixels within training areas. At the completion of this step, all training areas should be identified with respect to row and column coordinates within the image. 7th, for each spectral class, evaluate the training data using the tool available in the image processing system or the software that you are using. Assess uniformity of frequency histogram, class separability as difference matrix, the degree to which training data occupy the available spectral data space, and their visual appearance on the image. 8th, edit training fields to correct problems identified in step 7. Edit boundaries of training fields as needed. If necessary, discard those areas that are not suitable. Means many times when you check for the data set, or when you see the different samples, like if I take in different samples of the water, and if I find later on, if I find that there is some mistake in sample 2 and sample 3, it is better to remove those samples. Okay, remove those areas and thereafter continue the process. Finally, incorporate training data information into a form suitable for use in the classification procedure, and proceed with the classification process as described. Okay. So this is the idealized sequence of selecting training data. So we need to take care all these things when we are taking a sample. So this is how the first part is completed. The training stage is completed. Now, is there any question related to this training stage? Because from training, now we are going to the classification stage. If anybody of you have any confusion, anything that you have not, or you want to understand about the training stage, you can ask. Now there is a question from my side to all of you. Write down the question. Write down the question. If you are taking the samples for supervised classification, if you are taking samples for the supervised classification, then what are the key characteristics that you will consider? What are the key characteristics that you will consider while taking the samples? So we have learned a lot about the samples, about the precautions, about the characteristics that we need to take taken care of. So you quickly write down whatever you remember regarding the sampling procedure. I'm giving you just 2 minutes time. All of you write down in your copy what are the important things that you will consider while taking the samples. Yes, Megawat. Megawat.
Hello, ma'am. Yes, ma'am.
Yeah. So what you have
Ma'am,
written down?
ma'am, right now I'm in field, ma'am.
In field means?
Field means like agriculture field, ma'am.
So
So I'm not taking any copy and
what is the use of the class, Megawat, then? If you are in the agriculture field, you are not able to see your screen even, isn't it?
yes, ma'am. I'm little listening the class only, ma'am.
Yeah, so make sure that you will be in the class during the class sessions.
Yes, ma'am.
Okay, next, Parul.
Yes, ma'am. So the very first step is to see the image properly to identify the land cover present in an image, and then when we are marking the samples in an image, we should mark or assign samples to all the variation present in each land cover class. Then second, we should assign enough number of samples to each class, and it should be well distributed. And third, when we are marking the samples, we should zoom properly uh, in the image to classify the image free from the outliers. And yes, ma'am.
Okay. Next, Ruchi. Yes, Ruchi. Yeah, what you have written down?
Ma'am, external knowledge of the area and number of spectral bands, degree of variability presence in the class.
Mm-hmm. Okay.
And number of pixels, ma'am.
So I'm not written down completely. Try to remember what are the other things. Okay, autocorrelation, well distribution of the data set,
Ma'am,
absence of
shape
outlier.
and look.
Okay, write down all the things.
Okay.
Okay, so we have done with the training stage. Now we are moving towards the next, which is a classification stage. And in the classification stage, we are going to learn about the different methods that are used for supervised classification. So this will involve parallelepiped classifier, centroid classifier, Gaussian maximum likelihood classifier, and others. I am giving you 10 minutes break first, and after the break, I will start this topic. Okay, 10 minutes break. Let's start the class again. Am I audible?
Yes, ma'am.
Yes.
Okay. We are coming to the second stage of supervised classification. Okay. Write down the stages of supervised classification. What are the three different stages? Write down in your copy. What are the three different stages of supervised classification? Write down the answer of this question. What are the three different stages of supervised classification? Yes, Shivam,
Yes, ma'am.
what is the answer?
Ma'am, training stage, classification stage, and output stage.
Yeah. So these are the three stages of classification, and we have covered the first stage. Coming to the second stage, which involves the classification, means when you have given the training, when you have given the samples, there must be certain way through which we can assign a land use land cover to every pixel. In second stage, which is the classification stage, this task will be carried out. In this one, each pixel will be assigned some value. How this can be done? This can be, just wait for a minute. So this is done by different classifiers. The very first one is the parallelepiped classifier, which is also known as the decision box or decision rule, or it can be known as the level slicing procedure. There are different names through which we can give this parallelepiped classifier. In parallelepiped classification, what will happen? First of all, for every sample, as you can see in this example, I'll show you over here. So as you can see it over here, that there are different categories that you have learnt over here: water, sand, forest, urban, corn, hay. So these are the different categories. 6 categories are present. So when you go for the classification in the parallelepiped classifier or in a parallelepiped classification scheme, for every category, urban, water, sand, corn, hay, forest, you can see that there are boxes around them, isn't it? Around all these 6 category, there are boxes around each of the individual land use land cover class, LULC class. As you can see, the same for water, urban, sand, this box for corn, hay, and forest. How these boxes will be created? These are created by using the minimum and the maximum value. For every class, for every LULC category, the minimum and maximum value will be taken. On the basis of these values, these boxes are created. If it is a two-dimensional, then it will be a box. But since this one is an n-dimensional data, what you are right now visualizing, it is a simple two-dimensional data. But when we talk about the multispectral image, there is no, there can be 7 bands, 8 bands, 10 bands. So what will be the dimension of this box according to that one? So at most we can draw up to 3D, three-dimensional data set. But for the n channel, for the n bands, the dimension of this box, this simple box which is appearing on the screen, this will be the n dimensional, where n is the number of bands. That's why instead of using the term box, this big term, parallelepiped, is used over here. So this parallelepiped is showing the n dimensional box over here. Now, once this box is created, whatever value we have, okay, whatever pixel value corresponding to every pixel, there will be a dn value. So whatever dn value we have, it will be placed on the graph or on the scatter plot like this, And wherever it is falling, in whichever box it is falling, the appropriate category will be assigned. For example, 1 is falling inside the box of hay. Okay, so it will be, the value of 1 will be hay, or the category of 0.1 will be hay. Similarly, 2 is falling inside the box of urban. So the category of 2 will be urban. Okay, so this is how the parallel pipe classification will take place. If you see the advantage of this classification technique, then this technique is very simple. Just if you perform the coding of this section, that part is also very simple, because we are just need to create simple boxes by using the minimum and maximum value of every LUSC class. And based on that one, the boxes are created and the appropriate category is assigned to the pixel in whichever box it is falling inside. So this is what the advantage of this whole procedure, its simplicity. Then what will be the problem, or what are the disadvantages or challenges of this procedure? Anyone?
मैम ओवरलैपिंग जो हो रही है उसके.
Yes, there is an overlapping between the box of corn and hay. So if any of the point will fall inside the overlapping region, in that case, there will be a conflict. It will, like, instead of this place, if point 1 fall inside this box at this place where I have placed my cursor right now, then there will be an ambiguity over here, whether it will be corn or it will be hay. There is an ambiguous state, because there are the chances of overlapping among the different category boxes. So this is one of the problem. Any other problem?
Pixels falling out of the classes.
Yeah. So it is like an extension of the previous one, that if the pixel falls inside the space where there is no box, again there is an ambiguity. There is a, not ambiguity, there is a problem, because none of the class could be assigned to that pixel, because it is not getting fall inside any of the class. So if any of the point is falling inside the box, then it's okay, appropriate class will be assigned. But if it is falling outside the box, then there will be a problem. It will become unclassified. Yes. Anything else? Any other problem that you can see?
The classifier does not represent the actual spectral class because it consider only the maximum and minimum values.
Yes. It consider the maximum and minimum value, and whenever there is a term of maximum and minimum value, we all know there will be one definite problem, which is of outliers. There is a chances of outliers. That's why the use of a minimum and maximum usually creates problem, because of the outlier, because of the error which is present in the data. It may not be the correct representative box of that category. Okay, so this is another problem. Anything else? There is one more problem. Can you see the box of hay? What is happening with hay? There is a strong correlation between band 3 and band 4. Isn't it? That's why we are getting this type of pattern over here, because of a high positive correlation between band 1 and band 3 and band 4 for hay, and negative for water. So when you see that there is a very strong correlation, the box become unrepresentative. See the urban area. What we will see, it is coming in a circular manner, isn't it? What's this? We have already learned this correlation diagram, that when there is a high correlation, it will appear like this, negative correlation like this. And if the correlation is less, then it is appearing in a circular manner. This is what we have learned earlier in the SIP. Coming back to this point, coming back to this one, you can see when there is a high correlation among the different bands, the box size will become very large and it somewhat become unrepresentative for that class. But when there is a very low correlation, as you can see in case of urban, it is coming in a circular manner, more or less like in a circular manner. That's why we can say that urban is not correlated, or it is very less correlated or uncorrelated between band 3 and band 4. So it is creating a box which is more representative of the urban area. So this is what the problem with the parallelepiped classifier. Clear? Because if the box size is very large, then it will, like one is getting categorized into hay, but actually it is belonging to the corn. It is very much near to the corn. So this is what the problem is with the parallelepiped classifier. I'm just reading out this portion. So it is a very simple supervised classifier. It is trained by inspecting histograms of individual bands of the available training data. The upper and lower values on the histograms are identified and used to describe the brightness value range for each band for that class. Together, the range in all bands describes a multidimensional box or parallelepiped. The extreme values are used in the estimation of the position of the parallelepiped's boundaries, which define regions of the p-dimensional feature space that are identified with a particular land cover types. Class is assigned to each pixel as per following rule. If pixel does not lie inside any of the parallelepiped class, then it is taken as unknown type. If point lies inside just one of the parallelepiped, then it is labeled as the member of the class represented by that parallelepiped. If the point lies inside two or more overlapping parallelepiped, then decision becomes complicated. Minimum distance to mean or maximum likelihood classifier can be used. Means there can be utilization of some other classifier to resolve such type of ambiguity, but again, it is like an overhead. Then advantages, this technique is easy to program and it's relatively fast in operation. Disadvantage, if use only the minimum and maximum values of each class, these values may be unrepresentative of the actual spectral class that they represent. It is assumed that the shape of the region occupied by a class can be enclosed by a box, which is not correct. Classes showing high covariance are poorly described by the rectangular decision regions and also causes overlap. So you have seen the example of hay for this purpose. So is it clear to everyone? This parallelepiped classifier is clear to everyone? The classifier is very simple. It is just taking the minimum and maximum value. A box is created. Why does, another question is, why do we name this as a parallelepiped classifier? Because we create n-dimensional boxes over here. That's why this parallelepiped term is used. And based upon these boxes, in whichever box a point lies, the appropriate category or the category will be assigned according to that. Okay. Now, I'm coming to the next one. Next one is a centroid classifier. See the see the figure of centroid classifier or minimum distance to mean classifier and try to understand it by yourself. Description of the figure is already given in this slide. Read it by yourself and try to understand what is happening over here. We have learned about the parallelepiped classifier, the first one. Now we are coming to the second one, which is the centroid classifier or minimum distance to mean. Both names are used. Centroid classifier or minimum distance to mean classifier. See this diagram and try to understand how the classification will take place. So what is happening over here? In the previous classifier, in the parallelepiped classifier, what was happening? Only the minimum and the maximum values are considered, and rest of the values which are taken in the samples are not considered while doing the classification. Isn't it? Just the minimum and maximum values are considered. So when we go for a minimum distance to mean classifier, first the mean value is computed. So when you are going to compute a mean, it means that all the values that are taken in the sampling step are considered. So here the mean values are taken, the mean of this, like in this one, as you can see that there is a plus, plus, plus. For every category, you can see this plus symbol. So this is showing the mean position of that land use land cover category. So once the mean position is considered, for every pixel in which the classification need to be done, so the distance from the mean position is considered. If this distance, the appropriate category is assigned to this pixel according to the distance. So the whichever class is having a minimum distance, the category of that one will be assigned to that one. Like in this one, for the one, the minimum distance will be from 1. Okay, so it will be from 1. That's why the minimum distance is from con. So the category con will be assigned to 1. Okay, so basically it involves dividing the whole space according to the distance. So this is how the whole space will get partitioned according to the mean position. Is it clear to everyone how this partitioning is taking place? The samples are taken like this way. As you can see in this figure, the samples are taken, the mean positions are computed. Once the mean positions are computed, thereafter a whole space will be divided. How this division will take place? According to the distance. Like suppose there is a water and urban. Okay, so suppose up to this distance, okay, so suppose up to this distance, the category is water, and up to this one, the category is urban. So according to that, this whole space will be of water, and the rest of the space, like up to this, it will be urban. Okay, so the whole space is getting divided into the different sections. How this division is taking place? This division is taking place as it is shown over here on the basis of the distance from sample mean position. So the sample mean of each of the category will be computed, and according to that one, the whole area will get partitioned. At which place this will create a problem?
Edge.
Yes,
Same
certainly.
distance.
At the boundary position, it will be at the same distance from 2 or more. Like if there is a point at this place, okay. In this case, when there is a point which is lying at this position, it will have a same distance from the mean position of 3 categories. So this one will be the ambiguous case. So what we have learned in the parallelepiped classifier, if a point falls inside an overlapping region, then there will be an ambiguity. Similarly, in case of centroid classifier, if a point lies on the edge, on the boundary position, then it will be at the same distance from 2 or more classes. So it will create a problem, or it will create an ambiguity. Otherwise, this minimum distance to mean classifier is a good classifier as compared to the parallelepiped classifier, because it is taking a mean position. But the problem is the previous method was more simple computationally it was very fast. In this one, it will take time. Okay. A lot of computation is involved when we go for a minimum distance to mean classifier. So I'm reading it out. The centroid classifier or k-means classifier or minimum distance to means classifier method make use of all the data in each training class as it is based upon the nearest center decision rule. It works as following. The centroid of each class is computed. It is simply the mean of each of the p bands. It diminishes the influence of extreme values because the mean values are taken. The Euclidean distance from each unknown pixel is then the Euclidean distance for each unknown pixel is then calculated for each center in turn, and the pixel is given the label of the center to which its distance is smallest. Thus, the P space is divided into regions by a set of, just wait for a minute. There is some urgent meeting right now, so I'm leaving the class, and all of you try to complete this whole portion, okay, by yourself. I have covered the parallelepiped classifier, centroid classifier. So read the maximum likelihood classifier by yourself, and I will cover this whole thing in the Monday session. And Monday there is a quiz also. Okay. So thank you so much to all of you. The class is over for now.
Thank you, ma'am.
Thank you, ma'am.
Thank you.
Thank you.